here. Okay.
Okay, okay, thank you.
Now it's recording, right? Okay.
Yeah, now it's recording.
So okay. So so now what I've done is I just imported the 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 box, and I usually what I do is there are two ways. It's always better to move the moving the box is very hard. So for example, if I want to change the alignment of the box or change the way it's dropping, if I started changing this, because we are already made the auto mesh, right? So it's the first thing to do is to do the automation, then call, and then just meshing, accepting, and done. So I'm just wanting to show you what the problem is if I wanted, and after that I import the wall. It will be very hard because eventually we want to change the alignment of the box. So maybe it's perpendicular or vertical or just like in the assignment. So when we move this box, it's just going to move the nodes, right? So if I say this by part and then start moving it, you see, you will have the box here, still here. So it's always, it's easier to move the wall and have the box going vertically or diagonally. So so that's why I always try not to move the box, but go to shape measure, and then we can see from the assignment. I cannot actually remember the dimensions, but just give me a minute. I want to see it now, and files.
Actually, you can continue with whatever dimensions you have right now.
Yeah, I just got it. So yeah, it can just be 2000. It doesn't matter actually because we are eventually changing or taking the. No, this is the box actually. So it's just 3000, 3000, and then 100 for the deep. Then create. It doesn't matter, accept, and so now we can. I think I can do the one for the aluminum or the steel. So what we are going to do is first we are moving the wall. To move the wall, you can just select this by part, and then you can move it. So we can start moving the wall itself. So this is in the Z direction, and then we can. It's easier to just to see here. So it's saying this Z is this way. So if you press plus, it's going this way, and if you say minus, it's going the other way. So if we go into Y, we want it to be higher. So we go to Y, and then if this is Y in the down direction, if I press minus, it's going up here, right? So this is, so now we have the wall, right? So it's just easier this way. And for the drop, it doesn't matter actually the orientation, because from what I know, even if you are doing a fall, eventually it's a free fall, right? So the first thing to do for this calculation is it's very easy to find the calculator for the free fall. So you just type free fall calculator, and it will give you the speed, the initial speed that you want. So initial speed in the assignment is 0, and the height is 4 feet. So it's giving 4.89. This is the velocity, right? So it's already calculating the velocity for us. So we can treat this just like a crash, but here we want to move the box instead of moving the wall. So first thing to do is you go to model, and I always start by creating the boundary conditions. So in the boundary conditions, we want this to be fixed. So you just go to create by part, and you fix this one, and then apply. So when all of these are clicked, then this means that it will be fixed x in the x direction, y in the y direction, z in the z direction, and rx is the rotational by rx, and r rotational by y, and rotational by z. So you are fixing it in all the directions. But we also need to have another boundary condition for the box itself. So we're going to create another boundary condition, but now it will be free in the z direction, just like in the PDF. But now we are going to when you press by element and then propagate, it will give you like an angle, so it will be easier to select things. So so we are going to select only this face, and this will be free in the z direction. So you unclick the z direction, right? And then you say apply. So now we have this as our boundary condition. The other thing is you have to set to make a node set for the box. So you have to create a new node set for the box, and that is by doing by part create the box, and then you can name it, say, box, and then apply. So now we have the nodes of the box also as separate nodes, and we need this for the velocity, to define the velocity, because we don't define the velocity here. We define it because here, when you define anything, for example, for the, in the initial and then velocity, it's not giving us the way of selecting the nodes, right? So you are only here you are only selecting parts like the wall or anything, but like the one in PDF. So to initiate the velocity, we have to go from the keywords. So we are done here. We go to keywords, and the first thing to do is assigning materials and sections for the parts that you have. So now we have two parts. The L shell is our box, and the box solid is the solid that we did, which is the wall. So we can just rename them now as this is the box, and the sections. You go to new keyword section, and this is now giving this for the box. So we have to define the thickness and the solid, the thickness and the type. So mainly the main thing is the thickness here, and you go to accept, and then accept again. And the other thing is the material, and this material, you don't have to go and fill it all the way together, from the start, because we already did this in the assignment, the other assignment. You can just import it. So this will be a piecewise linear plasticity, so this one. And instead of filling all this here, you can go to material form, material database, and it will show nothing here, but you go to browse, and you just choose any of the models that you already did. So for example, we can go to, I have, I think, some of the models. Let me think where I put them. So I think it would be in here, Ls-Dyna. So this is all what I've done in assignment 5. So I can just import it. So I can maybe choose steel, and I have my old K file for steel here, and I can just open and then load, done. So it will fill it automatically. So it's just easier this way, and then accept. and then accept again. So now we have the box defined. We have the thickness and we have the material. We also do the same thing for the box solid, which is our block. So it's easier just to say block. And then we also go and choose new. And this will be new because this is not a thickness. This is rigid, right? So you just say new ID, and it's already solid. So it's already detected that it's a solid, and then accept. Go to material, and then new, and this one will be rigid, right? 30 rigid, or actually it's 20. And same, we can do the same thing here. Instead of filling this, so we have already, this is loaded. So it's smart enough to know if I have any solid here, and it will just fill it up here. You know, it will be easier. Accept. So now we defined the sections and we defined the materials, and then done. So now we have the sections, we have the parts, we have the materials. The next step is to define the velocity. So we go to initial. Instead of doing this one by one, you can just say collapse all. It's easier. And we go to initial. And then here we'll go to velocity. And because this is linking the set of nodes, it will link the ones that we just did for the box. So it's just looking here for the set of nodes that we need, and we'll say nodes read. This is the node that we did earlier, right? So done. So it already selected the box now, and we need to then define the velocity that we want. And this will be in the minus Z direction, right? Because this is Z. Z is going up. So to get, if you want it to drop, we just say minus, and this will be 4.89. And we have taken this from the, website that I've just showed you. So so this is taking the height and everything in its calculation. So so if we take this box very high, like 4 feet or 1 meter, as assignment said, it will just take too much time in the pre-processing and this in the post-processing, and this will generate a lot of problems. So eventually, the velocity that we are counting here is a velocity that we assigned at contact. So at contact, it will be 4.89 meters per second, or milliseconds per millimeters. So it's just the same. So instead of having very high, you can just do it here. And then so we set the velocity. Now we go to contacts, which is very important. So contact. So first it will be nodes to surface, and for nodes to surface, it is actually nodes to surface. So our nodes is the box, and our surface will be the block that we did. So here it will be not a set of nodes, which is 4 node set, and here the master will be the part ID that we did. So for this one, it will be the box. Done. And this one will be the block. And you can add resistance and everything else, but I think this is good enough. Done. And then you go to single surface, and single surface is important because it will not let this box, you know, the parts, the nodes in the box collide with each other. So you need to set contacts for the box in itself. And this one will be the part. So you just say for the box, and then done, and that's it. Accept, done. So so now for this model, now everything is set, but we have to do the database and the control. So the control, we control the termination. The most important thing is termination, but you can also set the accuracy as one. And this is repetitive things. So what I've done is I've made a model with these repetitive things already set. So I can just import the model, and instead of going through all of them every time, it's just easier to have a preset model with everything, you know, like control, termination, and everything, time steps and everything. So termination is very important, and this is in the end time. So end time is when the post processor is going to end, and it depends on how high you have the box, or when do you expect the collision to happen. And I think for this one, maybe 40 milliseconds is okay. We don't want to take too much time, or maybe 50 milliseconds. It doesn't matter actually. I think it will collide sometime. So done. And time stepping, we can just leave it 0.9 as it is. You don't have to change it. The other thing is now is the database. So the ASCII options. For the ASCII options, you can just do the same as the ones in the PDF. So for example, GLStat, you can just make it 4.1. And then NC force, and you can just nodal inverse force, and this is the output that the program is going to give you to interpret or to see the results. So this is the results that you want. So nodal displacement, velocity, acceleration data. And on point one is point one, it's saying like point one is 10 times, or every 0.1 millisecond, it's going to generate these data. So if you make this higher, for example, 1, so you will have like, if we made like 50 milliseconds, right? So this will generate 50 nodal data and everything. And we'll do the same thing for the D3 plot. So if you make it smaller, you will have more increments and you get accurate results. So, and then binary 3D plot. And here is the time interval between outputs, just like the ones that we just did. And we can make this something reasonable. So maybe 0.1, or just as you like. Yani, if you make like 500 milliseconds or very big numbers, you better do this like 1 or 0.5, because it will take too much time. But 0.1 for this one, maybe it's okay. And then the last thing is extend binary. And we change this to 1. I'm not sure what is this doing, but I've seen that in the internet they're changing this one, saying it's important, but I'm not really sure what it's actually doing. So I think this model is done now. So this is all the things that we did. So to recap, the most important things are the control, actually not control, but the contacts, the boundary, the materials, the initial, and all of this can be accessed from the part. So you start by the boundary. So you set the boundary conditions, and then you can set the nodes. And from the nodes, you can go to part. And from part, you can assign the sections and the materials for each one, so you don't get lost in the many things that you have to do. And then after that, you go to velocity initial. So you set the velocity for the nodes that you did. And after that, we go to contacts. So you determine the contacts. So now we are saying these nodes are will have a contact with this body. And you can see all of this using this display. Display is very important, just to check that you did everything right. So the contacts, it will show you the contacts. So this is, so you have contacts here and you have contacts here, and you can say none. It will take it out, and then you go to contacts, general. You have two contacts, automatic nodes to surface. So these nodes to this surface, and single surface. So these single surface by itself. So you say none, and then you go to initial, and this will tell you the velocity. If you have done the velocity right, you can just check it here. So you can just go in and see the arrows pointing that this body is going down, right? So you can just check it before, check everything before. So you say none, and then sets, you have these nodes. So this is the box node that we did. So now I think everything is okay. So you can just save it. So maybe you can just save it as a new, and you can just save it here. So let's say example 6.k. Just save it. Okay, save. So now we have it saved here. So what I've done, and as I've told in the lecture, is there is an easier way to do things. Some trials, and actually I just waited for the added termination time and everything. So this is the final results. So it will give you something like this. So this is the impact. And if you want to see the, for example, the von Mises stress, you can just see it here. So it will tell you at the moment of impact. So you can just target the moment of the impact. You see, and you can also from this one, from the history, you can see the total energy. Just plot. So this is the moment of impact, and then the energy goes down. And if you want to plot, for example, effective strain or stress or whatever, so you need to choose the box. So you can just choose by part and choose the box. So it's plotting for each node on the box. It's going to give you the strain, and you plot. This usually takes some time, because I think it's hard work for this computer and so on. I think you have to just wait for it. Actually, working with Dyna and these types of projects, it takes a lot of time just waiting. So it's a good idea just to have several projects at a time. So one you can have in the CNC24, and the other, working in other things. So now it's plotting each node. And for example, you can see you can also track each node by itself, and you can see if there is any node that goes beyond yield, and then you can know if this model is going to break, or if you are going to have any breaks in any place, and so on. So I also want to show you how to average the curves if you want to see the overall strain and stress and so on. So, but I think now you get the idea, the main idea of doing, of how to do this. And If you have any questions, I'm very willing to help if I can. Apparently, also, if you have fewer nodes at the meshing, you will have fewer curves. And also, one of the things that the one that took us some time is, determining if you want, the computational speed and the data and the size of the data and everything. Between that and between choosing smaller distance, and eventually, I think you'll get it. So yeah, so this is it. I'm just waiting. Let's wait more. Actually, let me pause the recording and just let you know after this is done. So let's pause it. Yeah. Hi. So after waiting some time, I think it just crashed. But anyway, after doing the plot, you have this operation. And from in this operation, you can do what you want by this with these curves. So you can get the maximum, you get the minimum, you can average the curves and whatever. So that's it. So this is all I have for now. And if you have any questions, you are welcome to ask me. And see you. Yo, take care.